Good morning, Year 9. I thought I'd add a little bit of narration to these slides so it feels a little bit more like I'm teaching and to give a bit more guidance to you as we go through. So I hope you're all well. I thought this week I would start with ohmic and non-ohmic resistors. We did cover this before Easter, but it would be a nice chance to recap, make sure you know where we are before we move on next week. Anyway, here we go. Okay, so we're going to start off with a practical that we did before Easter. We did 2 or 3 like this using a circuit very much like the one shown on the slide. In this case, we're looking at a filament bulb. But as you can see, I've placed an ammeter in series with the bulb so I can measure the current as it flows through the bulb. And I've also put a voltmeter in parallel with the bulb to measure the potential difference across the bulb. On the right-hand side, you can see the variable resistor. We use that to vary the voltage or potential difference across the bulb and hence the current. So what we're going to do in this practical is set this up, use the variable resistor to change the voltage and then measure the voltage and the current in the circuit. At the end of this practical, we plotted a graph showing the current against the voltage as shown here. And it asks on the slide, what do we notice about the shape of the graph and what does this tell you? Hopefully you'll remember that if we get a straight line that goes through the origin, then the current is directly proportional to the voltage. That means if I double the current, I would double the voltage. If I halve the current, I halve the voltage and so on. If we get this sort of graph, then we call it an ohmic resistor. It obeys Ohm's law. So what we're really looking at in these practicals is trying to find out whether each component is ohmic. In fact, when we completed the practical, we found we didn't get a straight line through the origin at all. The current voltage graph for a bulb is not straight and therefore is not ohmic. What we actually find is that as the voltage or potential difference across the bulb increases, the resistance also increases. So it means that the filament bulb doesn't give us an ohmic relationship. Going a little bit beyond that, the reason for this is because a filament bulb gets hot as you increase the potential difference across it. And we don't see this as much in our homes today because we have energy efficient bulbs, but this is what happens on a filament bulb. If you want to extend this further, then we know that as we increase the temperature across the bulb, because the voltage is making it getting hotter, then the atoms within the wire inside the bulb are going to vibrate, and it makes it more difficult for the electrons to flow. And if they are slowed down, then the resistance in effect is increasing. Either way, we know that filament bulbs are not ohmic, and it's to do with the fact that they get hot. Okay, so on this slide, I've just added that little sentence there. As the bulb gets hotter, the atoms in the metal vibrate more, impeding the flow of electrons. This means a lower current and therefore higher resistance. This phrase is just a really easy way of explaining what happens in filament bulbs, and particularly for those of you who may in the future go on to do A-level, it's a really nice little phrase that I quite often used to teach my students to summarise what they needed to say in just a couple of sentences. So these 2 slides here are showing how you compare the resistor or resistance wire graph with the filament lamp graph side by side. In our following lesson then, we did exactly the same practical, but instead of using a filament bulb, we used an LED or light emitting diode. And the reason we use a light emitting diode as opposed to just a regular diode is that obviously you can see it when it's switched on, so you know if it's working. But also because LEDs are used all over the place in everyday life, whether it's the little indicator button on your telly saying it's on, to LED lights that we now use in our homes and on cars. So they're everywhere, absolutely everywhere. They're very, very low energy. So it's the idea to use a component in class that we actually use in real life. So after the experiment, I also got you to plot a graph. In this case, again, current against potential difference. But in this example, I wanted a negative axis on here for voltage. So this is different to what we did for the filament bulb. And that's because in the experiment, I asked you to switch the LED round so that we had the current flowing first one way through the LED and then the other way through the LED, because I wanted to see whether or not it mattered which way round the diode sits in the circuit. So when we put the diode in the first time, we got results on our graph that looked a little bit like this. It's almost ohmic because we do tend to get quite close to a straight line for a diode. But you'll see that in this example it's offset, it doesn't go through the origin. So we can't really call it ohmic, it's not quite directly proportional. So when we turned the diode round, we saw that we didn't get any current at all, it went right down to zero. So in fact what we find is, in the other direction, there is no current flowing at all. This means that the resistance in this direction must be very high, and it completes the graph showing that it isn't an ohmic resistor. So the conclusion to this experiment was that the current will only flow one way through the diode. When the voltage or potential difference is negative, then no current flows. The resistance is very high. And this is particularly useful because we use diodes anywhere where we don't want the current to go the wrong way round a circuit. So for example, if you replace a battery in anything, you'll see that you have to put it in the right way round or it doesn't work. We use diodes to make sure of that because some components won't work if you put the current through the wrong way. In fact, some things like capacitors can even blow up, and it means that you destroy the electrical item that you're using. So really, really useful. They're also used, as we'll see later, to convert alternating currents into direct currents. So this slide then shows the three different components together. So you can see the graph for resistor or resistance wire, filament lamp and diode together. This is a very common exam question. I know it's not why we learn physics just for exams, but they do like to show these graphs to make sure that you can work out which one is which and label them correctly. Okay, so finally, once you've been through this PowerPoint, I've got a couple of things you could look at online. The BBC Bite-Size page that covers exactly the same topic, I've put the link up there, and it will also be on Show My Homework. The second one is a YouTube video, not Mr. Free Science Man this time. I've gone for an A-level YouTube site. It's really good, and although it is originally aimed at A-level, the material is exactly the same as you need for GCSE. And it just gives you something a little bit different to listen to. You might find that you find that more accessible. And then I have also put together a couple of questions for you to try, and I've attached a mark scheme at the bottom so you can have a work through those and then check your answers against. And then finally, the quiz online, and that's there so I can have a look and see how you're doing and what you've understood. Anyway, good luck for now, and I will send something out next week.